Okay, so what I want to work on today is a performance problem in my base layer related to how I deal with strings. So I want to go over real quick how the strings work, just so that anyone watching this in one piece will be able to kind of follow along the main ideas. The strings are by themselves immutable and have a length carried with them. So they're not C strings, they're not null terminated necessarily. And they're hold on, let me turn that off. They're not null terminated necessarily, and they come with a size. So I don't need to scan them to find out their size. That's just what my strings are. Then to build up larger strings with things like so I have things like this. So I can this function push f is pushing memory on onto my memory arena based on a format string. So I can use good old fashioned C style format strings to construct fairly uh, much. It's much easier to construct string expressions using format strings than to do it like one call at a time in C. C doesn't give you a lot of good tools for string construction, so this is about as good as it gets. I use the format string thing, and I can then use that to build one of my strings. So that is helpful. And I have these string lists, so I can chain these together, and I can start outputting to a data stream where I'm constructing a string. So whenever I want to write code that like stringizes something, like here's a data structure, turn it into text so that we can print it and blop it onto some, output stream or something, or a log, whatever. I just output it as the way I handle that is I use an arena and a string list. That way I can treat it like a stream of outgoing data and just put all that stuff on there. The string list is made up of nodes, so each individual push puts another node onto the list, which is a pointer and then one of those strings, right? It's just a chain of pointer, a singly linked list of nodes, each containing a static chunk of text. And then when the thing is done, all those separate nodes get concatenated together to form a final output stream, or they get copied out to a file, or they get copied out to the output stream, or whatever. Um, that's how it works. So there's a couple of layers to the there are good things about this and there's some bad things about it. The part I want to hold on to is I like the ability to express my string functions in such a way that I can use them as data. I don't like writing stringizing functions that just print straight out to a standard outstream, because that makes it much harder to then you know actually use that to package things up into larger data structures and reuse them. Being able to use this as not just a visualization but also a data conversion is an important part of it for me. But that creates friction in two places. One is that the API level stuff is not as good. So now, if I want to do something like um, put together, like, how do I want to put this? If I want to create a log that streams together a few of these, there's now these two different parameters I have to keep track of. It's just what I'm trying to say is that the two parameters make it harder to deal with, and there's a second layer of API friction there that's a little bit harder to grapple with. But the once you have a bunch of stringizers that output data, 80% of the time, what you want to do with them is print them. And so right now, in order to do that, I have to create one of like grab a scratch arena, grab a list, do some printing into that list. Right, I catch everything into this list, and then at the end, I can print the whole thing. And the boilerplate for grabbing a scratch and the boilerplate for grabbing the list and stringizing it at the end and then passing it like printing it, and the passing around of two parameters are just a bunch of API weight. Ultimately, it'd be nice to get all the way to the point where if I wrote a stringizing function, it could be used for data output or like streaming, printing out. I need to figure out how I'm going to distinguish these two concepts. Returning data, it could be used for returning data or for outputting it straight to a data stream, like a file stream, file handle. Um, that would be cool to be able to use this one call either way, because I don't want to have to. The annoying part is this. Let me pull up. Um, um, I want to go into the new one, but I don't know if SimNew actually has what I need. Print log. Yeah, that doesn't have it. Gonna have to go find it somewhere else. Okay, hold on. So my example code's in another project here. Just bear with me. Okay, I do have them loaded somewhere. The one I'm looking for is games operators. Where did I have printing functions? Oh, well, okay. I don't need to use this project. Let's go to the thing I was doing yesterday. The ASCII code has this. There's one call here that returns the string, and the way we return the string again is I pass in an arena and an output list and put the output data onto this output list. But that's just a way of returning a string, basically. It's a more convenient, more performant way to handle string output for this kind of return. But then I need a separate function that I declare with a different name and define with a little separate helper thing here that then passes all this along. It's not the worst thing ever, but the fact that now there's okay, if you were trying to do C standard library, if you were trying to eliminate it, you would now need a thing that's Mr. Whatever, standard IO, enable, what was the one that what's the name of it? But yeah, it's base standard IO, right? If we're doing standard IO, then do it, or something like this. Because if you want to be able to use my libraries without assuming a C standard library is tied in, which I would like to be able to always support, then it just gets all complicated. So before I can turn this into a full-on library, I have to have a good solution for all of my string printing stuff. This is one of the things that annoy me all the time. So I want to be able to use this, have one function that I implement once that uses my own type for every particular thing I print, right? So there'd be one for the histogram stats, one for the histogram itself, one for the table. Each one of these would be implemented separate, but they'd get one implementation each. There wouldn't be wrappers and helpers and so on. And they'd have a single parameter that's just a stream output. And that stream output can then trivially either be gathering up text as a string data structure to return to the user to use, or dispatching to a output stream, so that if you want to enable C standard stuff, it could all just dispatch to printf. It could all just write to the standard out handle. And I want to solve that today so that I don't have to keep writing all these layers of wrappers and wrappers. I just want to get it tidied up into one spot. Now you might be wondering, why bother doing that? Why not just use file all the time? Because probably there's a way to do file to string. Now, there probably is. I also wouldn't be surprised if there isn't. If there's not a way to use the file handles in C to construct a string, I wouldn't be that surprised. But I don't know the APIs that well. There probably is. But I still want to support going off of the C standard with all of this code. So either way, I have to implement my own. And I already, implement my own allocator for the arena. Why not also write the base allocator for a stream like this, right? So that's kind of the goal for today, is to replace this and this with one single print or something like that, or straight stringized stats. I'm not sure what I'll call it yet, but it'll be something like this. and it should be the only one I need from now on. And the default behavior for the stream will be that it's just going to be an optimized string output gathering thing that then has a way to be turned into a string at the end. Okay. So let's start. There's not a lot to diagram here. This is more of a bytes and pages and blocks. This is about inventory management and shuffling and linking things together and leaving notes in the right spot. This is a old school data structure problem. I'm going to do music. Okay, so there's a POSIX way to do it. Of course. That's also an option. I classified it, the problem, the classification I made for the problem, the question was either it exists or it doesn't exist, but there's always the possibility that they only did it on the Linux version, or the Unix path has the thing that makes the API make sense. Honestly, it's really puzzling to me how certain things end up in C standard and other things end up in, like, the way that the C language and Unix stuff blend together is still not fully familiar to me. I don't know, like, I don't know the history of how that happened. I don't know the decision-making process. I don't know how it feels like a mutant creature kind of thing. Like it sounds like it just barely holds together, almost Frankensteinian when I think about it. But I don't know. Maybe not. Maybe it makes perfect sense. I just haven't really seen how it all fits. Okay, so that's the main API we're looking for here, at least for the data structure of data blocks. The additional ambition of not having to do print wrappers, we'll maybe have to deal with that on another day possibly. I said I wanted to solve it, but that is a bit of a stretch goal. The main thing is getting this data structure up and running. Hello and welcome. Now, I'm basically assuming that this is probably going to be a sort of modified arena. It's going to be very arena-like, but it's going to be modified. The arena is close to being what I want already, but the stream is just going to be tuned for slightly different things in some ways, and it's going to be prepared to avoid. We're going to be set up to I mean, I definitely think we would still write this on the same API as Arena. So like they'd both be using operating system memory reserve and commit logic. I guess the question is, if I'm gonna be using this to gather up strings in small places, like if there are gonna be small string gathering tasks all over the place, then I don't want to have to allocate a new one. I'm expecting I might need more of these. Like these might need to be smaller and more lightweight. We might need to optimize the method of getting the pages, and we might want to tune the size of the pages down considerably from the Arena implementation. So with that in mind, I think the plan is to do something like this. Does my base layer have any threading stuff yet? Like, do I have mutexes? I don't. Wonderful. So this is the first time I wish I did. Code bases have to grow. Put it on the to-do list. I don't think I've done any tasks yet that needed thread safety, because I kind of stay away from this kind of thing a lot of the time. But for this data structure, I think that would be the right choice. I mean, for the longest time, I've just gotten away with 2 scratch arenas on each thread for most use cases. But for this, I'm thinking we go global vars, and we go like this, and then these will have a, whoops, next on them. So we'll come over here and we'll go stream free, and this right here okay, so that'll start off as a 0. We'll need a stream arena to live up here too. So this is the thing, the first thing that we would want to have a mutex around if I ever had multiple threads. I don't usually use global variables in ways that could be thread unsafe on purpose, without dealing with that. But here's why I'm stopping and making a big deal about it. Okay, so first time you get a stream, we'll create the arena for streams, then we'll allocate a stream, and from then on, whenever we need a stream we don't have one, we grab it off the arena. Streams themselves then will get released by going like this. This will also need to be in a critical section. Sucks so much though. If you put a critical section there, it just stops feeling like something lightweight. Like it doesn't work. But neither does going to the arena alloc. That's not lightweight either. I mean, this one would be a one-time thing. This would all be lightweight for after the first one. But if these are then in a critical section, it doesn't really feel lightweight to me, actually. Like, I want to be able to say, like, there might be right, so if you start using these, that's why you have to have this clear. You want to avoid going back to the... So if these won't be lightweight, then what would have to happen is you'd have to allocate a few ahead of time. And then use those over and over again for an algorithm. Like, I'm thinking of cases where, like, if you're building a table with, you know, rows and columns of text, and so you're creating like a stream to... Right, so what you would end up doing is instead of creating one stream for each cell and then submitting it all to the table, you'll say, well, stream creation isn't lightweight, actually. Streams take a little bit of time to set up and prepare. And so we push the granularity on them up to the large scale. We make one stream for an entire table, and then the table API provides the interconnect. The alternative is that each thread is equipped with a pool of streams separately. So if I want to avoid this, let's if zero out the comment And then also these globals. And let's try just a different tact here. What if instead I was thinking something more like thread var arena stream arena. That's an arena for each thread for the stream system. That seems like too much. But each thread is going to want multiple streams. Maybe it's more arenas, but it's not necessarily too much. Stream free. If stream arena equals 0, stream arena equals arena alloc. So the advantage of this is now it's lightweight. I mean, once per thread you arena alloc to get an arena. Okay, well, we can push further. This could still be global. So there could be one stream arena. This needs, so we do need critical sections. We would have crit begin, crit end, crit begin, crit end. So you get a critical section, but only under certain conditions now. If it's the first time on the in the whole program, then you might hit this critical section, and one of them will do the work of setting up an arena. And then each thread can hit this independently of each other and allocate off their own local pools. But if you get to the point where you find out you are trying to get a stream for your thread, but your thread's local pool is empty, then you go and wait for the critical section again. So you, on your first call of this, you'll get a little wait. But if you're constructing 100 little ones over and over and over again, well, if you need 100 separate streams, then that's not gonna, that you're gonna, for the first time you do it, you're gonna need to get a few of them together here. What I could do is sort of escalate the growth. So like if you get 1, then I give you 2, and then if you run out again, I give you 8, and so that it doesn't hit that critical section too many times. So we could do grow ahead to decrease crit section count. Well, Terry's Python, yes, but the check happens, and then a bunch of work happens inside this function, and then an assignment happens. So two things could both do the check at the same time, right? And then, like, I could finish my check, and then I go to sleep. You finish your check and allocate. And so that's why you put the check inside the section. Sure, the check is atomic, but the two threads could both complete the check before one of them does the assignment. Right. Yeah, critical sections is a weird way of programming. I don't know how it clicked in my head. It was like one specific day in a particular class at universities. One of the two things that I actually got out of going to college was, and I still missed semaphores. I've never understood semaphores. But I got like the condition variables. When I saw some examples of programming condition variables, I was like, I think I see the exact, like, crystallize exactly how the whole thing fits together. Yeah, so I'm not worried about contention issues too much, because there could be, if you have, a swarm of 64 cores all waking up, and they all have to go and create one of these at the same time. Yes, you'll have to have once per thread, you'll have to do a critical section handoff. That initial handshake will be slow. I think if you're doing lots of streams all the time, that's already a strange use case. It's more like you use one and then you release it over and over again is more of the common use case, I think. And maybe you grab a couple and release them, and then grab a couple and release them. So there's some kind of number that you're tending to use, and that's why I think something like exponentially increasing the number of streams that we allocate at once here might do the trick, and put them all onto the local free list. No, I haven't. I haven't read Colin's article on Futex, and I've heard of Futexes and read about them and thought about them, but I've never really fully got the concept of what to do with a Futex. Brett, well, I got to this through the RPG simulator project, but this is gonna go into my base layer. Um, the way we got to this was that I wanted to do some ASCII printing stuff yesterday, so I did a bunch of that. And then one of the other things I was concerned about when I was looking at that is just how I've always wanted to, but never gotten around to doing something a little bit more high performance for large string building processes. So that's what we're doing today. So it's connected because everything I do is connected in that way, but it's not exactly for the RPG project as much as it's for my code base. Okay. So writing out to the stream is easy. You just, well, first you have to stop imagining that you have already built the stream system. What's the data structure going to be? So we know we're grabbing these things and yeah, and again, I think that's probably the right solution. I think what I found confusing about it is that people always talk about it as resource allocation. And so to me, the picture I think I had in my head is that it's a counter that you can increment by one or decrement by one. And there's a range that that counter is allowed to stay inside of. And if you try to increment or decrement past the boundary, it makes you wait. And now that concept makes perfect sense to me. Like you're like, oh, I tried to add one, but there can only be four, and there's already four, so you have to wait till someone subtracts one before you can complete this add one. But then like that, so that picture makes perfect sense. Then it's actually more like an open close API though. It's like you take it and release it, so that's increment decrement, but the release is non-blocking, and so then I realized my picture is wrong. It's like it's probably only on the take that it blocks, and over releasing is wrong the same way it is with a mutex. But for whatever reason, in my head, it made more sense when I thought it was double sided, but then I found out that's not how it works, and kind of gave up, like shrugged it off. Okay. That makes sense. All right, what do I want inside one of these structures? It's gonna be kind of like an arena, like I was saying. It's gonna have I think I need like something like a stream block. And these will chain together. I think it'll be something like this. And so stream blocks themselves will probably also be like this. Okay, and so then when you go to write to one of these, the way you'll do it is you'll get a current stream block. If that block is 0, or if that block is filled, Negate is telling me that semaphores are a lot like the McDonald's table tents, which I don't even know if I know what that means. Okay, I know. I. Oh, do you mean like the number, the little the table number? Because if you were talking about table numbers, that would make sense. But if you're talking about like the overhead tent, I mean it all then that's a pretty spectacular metaphor. Okay. Okay, so if we got no block or if the block is full. Now I paused out right there because there's a difference between the how do I want to put this? The amount that is filled here is a kind of confusing concept. When I allocate a block, this is going to be the header of the block, right? This is going to, these 4 times 8, so 32 bytes, are going to make up the header of the block. And this amount filled, well, the reserve and commit are going to talk about literally on the memory. So we're going to initially have some amount reserved, and the first little bit of it will be committed to, and that'll be our block, right? That'll be where the block starts. And so there'll be 32 bytes filled at that level. But none of it, the stream will be empty. The total size of the stream will be empty. So it's like this, the total size is the sum of the filled size of each block minus the mandatory header size that's always filled on each block. And I think that's the right way to track it. That way these can just be direct comparisons, and these can be directly just one additional. They are arithmetic off of the main pointer without an additional bias, right? It's all just going to be based on the raw number of bytes. That's the plan. So we're going to need a little helper function here. It's going to be like this. Although I don't actually know if we want block release yet. That might be a little different from what I actually want. The stream new block though is definitely going to need to exist. I'll get into what that means in a minute. But then either way, once I've got a new block, I should be good to go, because we'll basically say that this must return a new block with space in it, and then we'll need to stick that new block onto the stream, and stream block. The block count will go up by 1. Mm-hmm. Yeah, I have a lot of visions of data structures I would build, but they're not actually quite practical. Practical data structures are locally well contained. It always ends up feeling like there's ways to build grand patterns spanning across multiple systems, but man, it's easy to screw that up. Real easy. And it's kind of unclear if it pays off. Okay, so once we've got a block, now we're basically in assert block does not equal 0, and block size filled is less than block size reserve territory. So now let's do copy amount equals the smaller of available space, which is block size reserve minus block size filled. And we're going to be tracking the position that we're copying to here, multiple steps through the loop. Available space is how much space there is in the block. Source size is data size minus the current position. Take the smaller of those two, memory copy into, now we cast the block pointer itself to a U8 so that we can add some pointer arithmetic, size filled, and we want to copy from data.string plus position the copy amount, and we want to increment the position by the copy amount after that. If that did not give us if that did not completely finish copying out data into the stream, it'll recur the loop again and grab another block and keep filling blocks. Yeah, that's a pretty cool system to gate. I think I've heard you explain that before, but it's pretty cool. All right. Copy amount. So the only problem here is, okay, after I've done that, the block size filled has to increment by that amount. Now, something else has to happen, which is here we're going to calculate amount we can copy. Make sure we've got a block to fill. Make sure the block is committed enough. So for that, what we have to do is go new size filled is going to be the block current size filled plus the copy amount. If that is going to be greater than the commit amount, then we need to increase the commit amount. We should already have that it's possible to increase the commit amount because we're only calculating copy amount large enough that it fits within the reserve in the first place. So we need to calculate a new size commit by going align pow2 what did I call this? Is it align up pow2? There it is. Align up. I need to go through and think through the naming scheme on some of my rounding functions. Actually, that's something I've never done, and they're not all very consistent. And this one's like macro naming scheme for some reason. I don't know why. Align up power 2. What is the size? I think I did this in the arena implementations here. Mem commit block size. Yes. We're not going to use that default reserve size, but we'll take the mem commit block size. Well, is that really? This is very much about, I don't know if I want to commit 64 blocks at a time. I can commit less than that. I'm going to just set up new macros for this one to tune it up myself, I guess. So for reserve size, I think we should grab like 4 megabytes at a time. And for commit size, I'm just counting out in my head. This allowed us to make many, many blocks. And I'm not usually printing out a gigabyte, but if I am, how many times do you have to repeat this? 1024, 512, 256, about 256 repetitions of this to get to a gigabyte. Hey, welcome. Yeah, 64 commit size of 64 at a time. I think with things like this, it might make sense to do new commit size is the current commit size times 2. Because then we could do like 16 here. But then, of course, if it's going to be something like this, kind of feels like it makes sense. Okay, the commit size is new size commit minus the current size commit. And then we want to do OS memory commit. Here we got to look at the block, beginning of the block plus the block's size commit with an amount equal to the commit size. And if that works, do that. Okay. Copy, memory, and advanced counters. That's good. So this should work once I finish the rest of the functions. This gives me the loop that copies data out of the string we got and fills in the blocks. Now, this one's easy. This is just unless I could dig under below a layer to avoid the temp there. Let's do this. Let's dig one layer below and actually have an independent FV implementation here. But this will allow this to go faster, so seems good. Copy the args. First time through. Arena temp scratch equals arena get scratch. Well, hold on. If this ends up having to use an arena anyways. Okay. Buffer size equals. Let's just think about how we would do this on top of the stream. Let's grab the current block. So the buffer size is going to be the block. This is where we do this. Buffer size. Is the block's size committed minus the block's size filled? That's how much space there is in the buffer. The buffer starts at block plus size filled. Now, if the first try worked, increment block size. Block size filled plus equals actual size. If the first try failed, reset and try again with the correct size. So here's where what we're going to have to do is grab. Now we give up. We go arena get scratch. Arena release scratch. We just need, we don't know how much we need until we get here and see the actual size. So now we can get the actual size. There's the buffer. Oh, you like to do it that way? That's cool. And then instead of returning this, we're going to do stream right. So we just construct the string. We didn't have enough space. Either the commit needs to grow or the block is too small and the stream needs to grow. But one way or another, the growth logic is contained here inside of stream right, whereas stream right FV is trying to do a quick path. And the quick path would be this, like first grab a block. Hopefully the block exists and it's ready to go. And hopefully it has enough space to just fill in, and then no work has to happen. No arena needs to be grabbed. No other functions have to get called, so we just go into filling the buffer and move on, right? But sometimes there won't be enough space. A lot of times there might be, but sometimes there won't be enough space, and so then we fall back to the slower path. We're already in the slow case, so then we use the high-level code that directs us into growing and filling a large string into the space. So that should be good as a nice first pass. And then we still need the right F function, which I started with, but then decided I wanted to do it directly on a FV function instead of using the usual method I would have done, which is to just go through the Scratch arena like this. So that's just calling to that. That avoids trying to use an arena at all and just puts the data straight into the block as often as possible. So stream clear is going to involve releasing the chain of blocks and setting the block count and size back to 0. And so to do this, you have to go let's see, if the stream first block does not equal 0, then what has to happen is the stream last block's next pointer becomes the free stream block chain. So that points to the rest of the free block chain, and then the free block chain moves ahead to the front of that list. And then the first and last blocks get forgotten from the stream. So that clears out a list. And whenever we go to release a stream, we should also be clearing it. And then to read the stream, what you have to do is, well, there's a couple ways we could think about reading the stream. One is I could say, hey, I want to just scan across the blocks like I would with a so the way you read a single block is you go you take the U8 of the block and you add in the size of the block header. And then for the size of the string, you get the block's size filled minus the size of the header. And then to read the whole thing, what you do is you go allocate that much memory, and then you walk the blocks block +1. That's actually a better shorthand for the idea. That block size filled minus the size of the block itself. And there you go. So you can walk the blocks yourself if you want and print them out to some other data structure, or you can hand it an arena. It'll arrange it all for you. And then we can add in if... I don't know. I'm going to come back to the question of printing these on another pass. Let's get the block new done first. So this part is... the reason I didn't put it right in line here was first of all because I duplicated it here, but also because I was worried it might need a critical section, but actually it doesn't. We're using a local here, so we're using a thread local. Block is the stream block free. The allure to condense these into one type is so strong, and I think I'm going to go for it. It always feels right afterwards, so we're going to do that too. But not yet. There's still something. The block... The block new needs to go... And here's where we need another crit section. So I was right. I do need another critical section for the arena here, because we're going on to the stream arena, and we're grabbing this much. Nope, I'm wrong. I don't want that. Okay, the reason I don't need a critical section is because I'm going to instead be doing OS memory reserve. Right. Reserve size. Okay, this is a rough start, but it's something. Critical section is just a dumb word that it means a mutex or a lock. Although when I think of critical section, instead of thinking of the lock itself, I mean like this path of code is a critical section, is the same thing as saying to make it correct, this code needs to have mutex take and mutex release happening. So if this is required to make the code correct, then this is a critical section. That's the way my brain uses the term. I think other people are using it that way when you hear them say it, but who knows? Okay. Weird, I thought we were calling block new earlier. Is it new block up here? Yeah. Block new. Okay, and I want to change this just slightly. Block new. I don't want to have to commit multiple times, so when we get a block new, we'll do that. We'll do it like this. Although, you know, a better way to do this might be to just freaking stick a stream on it. Right, and just be like, all of this is just what the function is also doing. So this becomes stream block new, give it the stream, get the block back, and then all of that can be contained down here. Except, yeah, we want to grab this. So here's our commit size. So determine commit size, allocate block, put block on the stream chain. Init block. There we go. And this one can also simplify. Okay. Now, we've written all this code today, and it's just now occurred to me that I never actually included this code into the main program. So now we can track down my errors. There are going to be some. Give it the stream. Okay, give it the string 8 constructed out of the buffer and the size. Okay, compilation works. So now, let me try to rewrite some of the ASCII stuff on top of that and see how it feels. Well, just be inclusive. There we go. Stats is actually super boring. Okay. So what this would mean is instead of string list style for printing things, we would be going, okay, so the cool thing is this, at this level, I actually was already doing things in a chunk. So this makes very little difference to this histogram version of the printing thing. This would just become stream right, stream right. This is the only thing that's changing, is this. Although now that we're not passing in an arena, this doesn't have to avoid conflicts with that. So far all I've achieved is that send the grid out to the grid string. Output. Okay. I think if I push on this a little bit, I might get to the point where there doesn't need to be any right, this goes on Scratch now. That's interesting. So what I guess this is telling me is sometimes it would be better to get the data from the stream and fill it. So this would be like function void star stream alloc. But the problem with that is it's not always possible. Right? If what comes back is, if the size is too big, it just won't fit into the outgoing stream, which is why you don't do that. You arrange it into a grid first. And you submit it. And so actually this hasn't changed a thing because it used to not have to do that because the string nodes could be any size. There was a way where you could say the arena and this is so interesting. Look, the string list worked better here. But it's not going to work better very often. So I just need to figure out what it would take to make this work some of the time. So the grid is usually not so big that it would create a problem here, but occasionally the problem is that the grid's memory would go past the end of one block and into the next block. The arena doesn't have this problem because it uses blocks so freaking big that it doesn't matter, and we don't force them to be uniform. So if I ask for something huge, it would just create a new block and have that much memory in it anyways. The stream, I was trying to write it with the idea that the blocks could be more uniform because we're really trying to optimize out how there are little strings of like 1 to 5 to 20 bytes at a time coming out. And in that case, the stream is going to help because we're not going to have a node for each of those couple of bytes that we're streaming out, we're going to be able to just put it into an output buffer. But then in between those, there are times where I might just want to say, hey, I've got okay, so this is what needs to happen to make this compatible. What this will do is either this will fit into the current block, or it'll make a special block just big enough for this piece. Or, you know, if this is smaller than a block, then if it doesn't fit into the current block, it'll just make a new block and put it there. But if it needs to make a block bigger than it normally does, then it can. Okay. So here, where to go? Get a block. This is going to work a little differently. If we get a block and it's 0, then we'll do, well, yeah, this is just saying if it's 0 or if it's filled. Either way, we need something. Then what we're going to do is check if this block can give the memory. If block size filled plus size, let's do if block size reserve minus size filled is greater than or equal to the size, then result can equal the block plus the size filled, and then we increment that. So we just set aside some space. If So if we don't have enough room to have that much capacity in that block, then Then we take reserve min and we round it up to the next power of 2. That's now the reserve size. Then that's the commit size. Okay. Reserve, we commit, we make the block. Commit size, reserve size. We stick it on the thing, and there we go. And now, if we are allocating a head, what that means is we got here by going stream block new. It needs to be able to have a capacity for this much memory. We tried once, our first block just didn't have capacity. We don't want to waste time looking at more blocks that don't have capacity. Please give me at least this much capacity, etc., etc., etc. Here's the new block. And then you do this thing. Why don't we just do give the memory, and then this is I had it and I deleted it. Okay. What is this? This isn't if result is 0. This is if the block size filled plus size is greater than the blocked reserve size. Then we make a new block. We also want to say if the block hasn't committed all the memory, commit the memory. So if the block size filled plus size is greater than the block commit size, so this is kind of like this. New size filled, commit the memory, and then we hand over the memory. This becomes new size filled, although it would make me more comfortable to actually add in the size here, because so here we can assert block does not equal 0 and block and new size filled is less than the block's reserve size, and the new size filled is less than the block's commit size. And then
Give it away. That's good. But what's the Oh, right. The thought is the stream has a total size that I want to track as well. Whenever I'm dishing out anything to the block sizes, I should also be dishing out to the total size. Now this is just the default one, so it should keep using the default reserve size. What else we got? Same thing with you. This one should be using the get a block. This should work because well, this is saying if it's filled, but this is just saying if there's room. It's kind of the same thing. If we've got a block, if we don't have a block, or if we do have a block without enough size, then we get one with the right size. If the block hasn't committed all the memory, commit the memory, give the memory. Reserve size? Oh. Size reserve then. Size commit. Got my vocab words flipped. Okay, so the ASCII layer has this print function, which I can now write as something a little different. Okay. And for now, we'll close the loop out here by just building the file in here, although we actually want to go in a different direction with that so that these functions can be eliminated completely. But day one stuff. Stream, fprint. Stream. And the problem, the real problem here is if I do stream allocate ahead, then there's no way I can do file streaming under the hood without tweaking that a little bit, because if this is a file stream under the hood, you can't allocate ahead in a file stream and then fill it with how you like before you move on, unless you tweak the API at least. For this part, we just need to loop the blocks and write, what is it called? Oh, I guess I just do this. Block +1. The 1 block's size filled minus size of a block file. Okay, cool. I got everything working again. I'm going to take a 5 to 10 minute break here. When I get back, we'll talk about some final steps for today, but I think this will be a quick one. I just wanted to get the break ground on this problem, and so I've got something in there, and I'll be able to perk on it for a few weeks, and maybe we'll come back and address the second layer of the problem that I was talking about, the not wanting to have to write the print stuff, but I don't want to take too much longer, so we'll do a short break and we'll come back for maybe 20-30 minutes of just double checking everything, maybe figuring out how to work this through and play with it and test it and stretch it. But yeah, I think this will be good for today. So I'll be back shortly.
Okay, so we can do the same thing on the level of table for now if you want. So in the end there, the stream is basically identical right now to the string list for something like the histogram. All right, for the purposes of the histogram, I just grab a grid and fill it, and there's no extra copy. It's just grab the grid and fill. And that was the same with the string list, because with the string list, you'd grab the grid memory from an arena, fill it, and then pass that arena, like hook that arena into a string list. That was how you did everything. So that was not special there. Here with the stream, I added the special idea of allocate ahead. I think I want to tweak the API preemptively. And the way it would work is whenever you allocate ahead, you have to close that out before you print anything else. So you allocate ahead, which means you want to fill a certain size. So you grab the memory that you're going to fill, and then you fill it. And then when you're done filling it, you say, I want to commit that allocation to the stream. Now, the way that'll work is for the actual data structure, it's currently going to do nothing. It could be that it has a little runtime check to be like, have we closed one of these, right? We could do a little bit of API sanitization work with this closing thing, even when we're using the underlying data structure. But if later I want the stream to also be able to stand for just sending data straight out to a file handle or a socket or whatever else, then I'm going to want to be able to say allocate ahead is actually just sort of a local allocate on an arena, maybe a thread arena or something. Maybe the stream will have a small allocation available. Maybe it'll just go straight to the heap whenever you do that. I don't know what it'll do. But the point is, it's got to get you some memory that you'll use, and then you'll be when you say you're done with it, it'll take the memory you filled and submit that to the thing, because something like the file stream and the socket aren't going to let me allocate ahead innately, so I got to like implement that on top of them. All right. But this doesn't let you specify things out of order. It just lets you allocate things before you know what to put in before you've arranged the data that describes how to fill that memory, right? With all of these, what we're doing is we're actually copying in small strings. This is the one way to do it without copying in a small string. Okay. So let's try and apply the stream thing to the table for now. I think it's down at the very end, just when I allocate the grid, right? It's the same thing as the histogram, actually. We're just doing allocate ahead. And then instead of sending it to the output list, we just have to commit the allocation to the stream at the end. Right. All right, so I think that's good. Although, yeah, that's going to change a few minor things here and there.
Oh, I didn't implement stream commit allocation. There. Now it's implemented. Right, this simplifies down to stream release. Okay. I said I wanted to stop, but I'm sitting here staring at it, and I can't stop thinking about fixing this so that I don't have to, switch back and forth. I just want to get to the point where this function here alone would have everything it needs, would be everything that it needs. It already is everything that it needs to be. I just need it to work without me having to wrap it in the F print, right? I just want to get to the point where I don't need these wrappers. That's what I'm trying to say. So I think I'm gonna actually push in that direction, but well, okay, yeah, that's working too. I mean, this shows every sign that the allocate ahead is working. Let me think if there's... I would have to switch over to, like, RPG Simulator or something. And rewrite a little bit of that. Why don't we do that? I need to test it before I move on a little more thoroughly and see how it feels to integrate somewhere. So maybe somewhere around here. Let's load this project. So now we're in here, and we're going to look for... Okay, logging functions is promising, but it looks like that's all being rendered out through log F already, so that's not going to change that API. It's just going to be a matter of swapping out an implementation. I think that's a good place to start. Let's look at what's going on in the context for the logging. This is weird. So log straight, log F, indent. I think all of these should be considered part of the context layer. And not a part of the game logging layer. But at the point we get to character and set log state and read log are also okay. I see. It's worse than I thought. That's context layer logging. This is context layer logging. This one function was the one function that didn't belong, and it dragged all of them to the wrong layer. Crazy. Okay, so there's that little tweak on how I arrange the log. Now, you can see here it's outputting to a log arena and log string. Let's just go and replace that with a stream called the log. And then in SimCNew, you just need to make sure that you grab the new Mr. Forth stream file. For header and C file, there we go. Now you just need to do log equals stream new. Okay, we need to be able to do stream total size context log is greater than 0. Here we go. So this is good. This is what we need. We need something. So these are the write functions. These are the read functions. I'll make clear special. It's the only one that isn't basically some way or another of appending more onto the stream. You're out. Construct and release. Write functions. Read functions. These are out of order. Okay. Read functions, then there's standard IO, and there's helpers. Okay. So we need stream total size. That's actually not going to be a function. That's going to be a macro because it's literally just like it's right. It's like it's right there. Like that's it. No function. So what this is trying to do is peek at the last character. So let's just... well, let's read through a couple of these issues and see. So that's going to become just stream right F. No, just stream right stream and then a certain number of spaces. The stream is the context log. This one, that should just work now. Yeah, we know that one's not ready. What else do we have going on? Yeah. What else do we have going on? So, push copy, list push. So this is the substring. Okay, so you just want to write that much, right? So you want to do something like stream write this substring, right? That's the main idea. We want to write that into the stream. I already have built-in copies now, so that was a handwritten copy, but now it'll do the copy like that. Oh. Yeah, okay, I've got a couple ideas. I know where we need to put in the effort next. All right, let's just finish some of this integration stuff we were playing at, and then we'll go deal with more upgrades to the stream. Right, so I'm looking through errors to locate... Okay, when you want to read the log, all you have to do is stream read the log now. Is that it? That's everything you have to say? Yeah, so now this is the only issue. I think we just replace this with something like u8 last char equals stream peak last char. Right? I mean, that's very specialized. You could imagine just doing peak char and then, you know, -1, like making an indexing system and all that. It's doable, but all of the cases besides the last character are quite a bit more difficult. Like, they could be in a previous block, right? If it's not in the last, if the character you're looking for isn't already in the last block, then it's lost somewhere in the chain. This data structure isn't really set up for reading substrings rapidly, right? The best you could do is if you were going to do lots of reads for a long time and you didn't want to have to rearrange it into a single buffer to do that, you could set up some data structure that you can binary search or something, so you could get it better if you wanted to put it into read mode. But it's not a read data structure; it's a write data structure. So I think I'd rather just not go for the general case at all, because then I can just write a very simple solution to peak last char, and that incentivizes you to stick within that limit, because if you need more, it's going to get tricky. But we could make last char guaranteed a little faster than average, right? That's a special case. Now, the only tricky part here is what if the block is empty? That would be really strange, because the only time new blocks get put there is when we want to fill them with something. You have to allocate a head. Right F, right F, V, right. Yeah, okay. I have some ideas coming to me. Cool. Okay. Um, for now, to do peak last, we can say that the last block being empty is kind of an error case. I'm not sure I want to assert on it, but we'll just say if the stream last block, well, let's grab the block. And the block's size filled has to be greater than just the header, right? Then what we're interested in is the spot at the block is an array of U8, so we want to index the one at the size -1 and return it. Okay, so that's a crash. What happened there? I am attempting to integrate the stream, so a crash indicates something like, well, what does it do? This is the wrong project now. I am now switching between two Remedy projects. Here we go. RPG Simulator. Here we go. Show me the crash. Block new. The block. Commit size. Reserve size. Oh, whoops. That's funny. Okay, so let me think this through real quick. If log straight wants to look at the string and say, do this work, and then write to the log. The log currently has nothing in it. But then it comes in here. The data, it should be fine. Okay. So that should at least give me... Okay, reserve size is correct. Commit size is less than reserve min. Okay, I think I did it wrong. I think I should have said data.size here or something like that, right? Like if I actually think about what's relevant or just 0, I'm saying like just give me the default. I don't want to have an initial capacity requirement. Because that makes it commit and behave differently. There we go. Now why didn't that crash on the other one? Don't exactly know. But in the end, what it took to convert that was I had to add in a function for this last character thing. And we ultimately, through the RPG, just use this read log thing, which I can implement pretty easily. But that's just so I can ultimately print it. So what if this wanted to be... Well, that's the business of the RPG simulator. I'll decide that some other day. Let's go back to... stream. Okay, so there's something cool to do here before I wrap up for today. And that is I need to change a couple things about how this all works. So like I was saying, I think we can merge these together. And there's a possibility here for making the allocate ahead less of a problem that I didn't foresee at first. Well, there's still a problem. The stream needs to act like an arena at that moment, and it's a little bit hard for it to do that without having an arena in it. It's like right on the edge of working, though. I think it can be done. It's just a pain. Okay, so let's see. I want to just merge this together. So these already both have a next, so that's good. If I do something like this, then each stream is a header. I'm going to say... we want to have a pointer to the string. We'll call this the stream data, instead of it just being based off of the beginning of the block. It's a header, but I'm gonna also have a pointer to it so that it doesn't have to be a header the same way all the time. And then it's going to have a position to replace the size filled. It's going to have, this will be, call it position, commit position, and reserve position maybe. Reserve size. Now, a couple other things we can do here. These don't need to be strangers to each other. They can be the same pointer, right? They don't have to be packed separately. Actually, we don't need a first block. What we need is a next and a last block. The first block is myself, and the last block is tracked right here. All the in-between blocks have a last block for no good reason. They just are ignoring it. They all have a void data right here. That way they can either point to the end of the header, and then we just use we use position and commit position and reserve size all the same way. They're all relative to the head. Like, this is still a header with respect to the positions of these, but this points to the beginning of the actual data. And we don't want to eliminate that because sometimes that won't actually be, like, we'll use the data structure in a different way. We'll be able to point to data from somewhere else that got handed to us and just hold on to it in the chain. And then these will all just get set to the size of that data. So they won't be able to grow the reserve or anything. We'll just treat it like prepare data in memory that got handed to us. But when we want to, these can be growing memory blocks. The first one needs these three things special. The rest of them don't use that. There's danger if I start doing stuff like this. As long as all the stream blocks are big enough to contain one of these, this is fine. And the void data will point to the end of that if it's necessary to reserve the extra space. The data itself. But then how do we know what the full size thing is, right? Oh, that doesn't quite work. You need some way to know what the size of the thing is, right? So we need data, we need size. Now, if this is the header for a stream block, right, so each of these should have, it's tough. The hard part is I want to be able to stick a thing in there where the void pointer points anywhere. The size is just some data. And so if you have a big chunk you want to add in without having to do a copy, you can. That's what I'm trying to pull off. And in order to pull that off, there'll need to be a way to allocate one of these as a small thing. And then there'll also be a need to allocate them as big things. And the question is, how will you free them all? They can't get freed as a chain all at once because they definitely don't all belong in the same spot. If the small thing does not know at least enough information to determine whether or not it also contains a block of data with it, then it's a problem. So I think you need a capacity here. And that's the same thing as the reserve size. This is like the block reserve, which is not referring to this at all. It's referring to this. So if the smallest node is this big, then these can be 0 to say there is no block. And these can be 0 to say that this is... If we have this is 1, 2, 3, 4, 5. So this is 40 bytes. This is 48, 50. This is 64 bytes. I feel like this should just be the size of the small block. Actually, the small node. Even though the smallest version would only use these 3 fields and the rest would be null because they're not relevant, having them separated into separate types is just going to make all the rest of the coding so much harder. When we want to transition between using them interchangeably and treating them specially. The only remaining issue is when you go to free a chain, I think you're going to have to pick it apart one element at a time. I think a process of freeing it's going to have to happen. Because some of them might be these small nodes. And they shouldn't remain linked to each other when they go onto the free list. So something we could do is, if we're going to have small nodes and they only need this much of the space, they could have a separate chain running through them so they can all just be pulled out over there. You still scan the whole list once. And anything that's a big block, you pop it off. Like you go insert it into the free list of big blocks. Anything that's a mega big block, you release it. Anything that's a normal size block, you stick it into the free list. Anything that's a mini block, you leave it alone. And then all the mini blocks go at once. But you have to scan the whole list once, I guess. Unless the next pointer... Okay, there are ways to do it. There are so totally ways to do it. It's just that we would need a couple of different nexts. We would need we'd have to track a couple of these. It's going to make the stream node bigger, but a lot of these are not necessary. Let me just picture this for a minute. There are two chains of free lists, both of the same type, but they are linked across a different. They have a next pointer. Then when you make a chain, the next one in the chain is one type of thing, and then the next one of the same kind is the other. Right, so no, I don't use a Git client. I just type in Git commands. I have like 3 Git commands memorized, and that's about it. That's my Git workflow. Okay, so I am going to use a second type. And it's going to be a little bigger. So a node is 1, 2, 3, 4, 5, 6, but some block nodes are much bigger, and so they have space for more, and some block nodes will have this whenever they're created by this stream new directly. And that will look like stream the first one can't be of both types. So I used to be able to get away with not having a first pointer because the stream node that you're passing around itself works. Like if you have the header to this, you already have the first one. Now that's not true if I need to know where the first of each type of node is. Hold on, let me just try this out. So first order, stream last order, stream first mini, stream last mini, stream first block, stream last block. So complicated all of a sudden, huh? Now with this, it would be able to free without having to iterate the chain, because it would just look at this chain and move it from one spot to another, look at this chain and move it from one spot to another, and it would be done. It could maybe still want to scan the blocks to free some of them, to reduce the amount of memory being carried. But then we also still need the total size. We don't actually need a block count, so we could drop that. With this much, I guess we already know about the first one in order. With this much, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 96 bytes for each thing I want to stick on here. Okay, what if we simplify some on some other fronts for now? Let's try to build up to this by saying the advantage here is now if the first thing you put on a stream is actually an outside data block, that can work, except when you create a new one, you create a new empty one, it assumes you're gonna fill it with man, I remember the day when I figured out the string list thing, the way of outputting stuff with an arena in a string list. I was really like relieved because there's always this issue of like when you're trying to do it this way, you kind of you optimize a common case, but you do really make it hard to fit in another type of high performance behavior of just linking in data that already exists without a copy. All right, eliminating those copies is a whole extra step of complexity, and the string list approach just 100% solves that, no question. That's because it can just link these together without as many of these together as you want. Linking those together is easy, but then throwing in a capacity. So the idea here would be if this is non-zero, then this block is a data block and not, node is a data block and not just a data pointer. And so you know in that case that as long as data, this data pointer plus this size won't go past this point, you can continue adding data in and increasing the size. And then if this is null, you know that this is just non-immutable data that you aren't allowed to touch. Now, if you want to free that, you need to be able to put them into different places because your blocks want to get reused together, and the little ones will have to come out of some other allocation for you, like another free list of streams altogether. So they need different starting point. So then the issue becomes if I create one of these, what do I make first? What if I'm going to attach data right away? So a totally different approach I could take is to say, let's just play with a different idea here. I'm gonna just keep playing with this because I feel like something's off about how hard this is feeling. What if I let the arena continue to manage the memory, and we're gonna have stream nodes, which will look like this. And then sometimes we'll be in a state where the last node is buffer. We'll call this buffer mode. And when it's in buffer mode, that means that there's a node set here that is able to grow. And there's a... okay, so we're in buffer mode. So there will be a buffer mode whenever buffer cap is non-zero. Then this can grow, and we can add more data there. When the time comes to free the whole stream, or to like release a stream, what we're going to do is clear the arena and then put the stream back to... We could just clear the arena. What's sad about this is now there's a full arena alloc and release with each new arena, and I'd love to be able to have a pool of streams that are already set to go. But this feels like it's going to simplify things. I won't have to deal with the commit growth, because that'll just be in the arena. And we'll have slightly large chunks ahead, going ahead, but like this will be out. This will, yeah, let's simplify and come at it again from a different angle. This is feeling better. So this is going to be, there's not going to need to be a critical section at all. For now, a stream is just allocated onto an arena. And then we're good to go. We do want to keep a total size going as well. When we release it, we'll clear it and nothing else. When we clear it, we'll arena pop to 0 on our streams arena, and we'll set first, we'll memory 0 struct the stream, except we have to save the arena in between. Then we can restore the arena. Okay. Current position, grab the arena, clear it back to that position. Move 0 the stream, put it back together. That's how you clear an arena stream now. Okay. Get some buffer to fill. If the stream is in buffer mode, if the stream is in buffer mode, then what we do is we buffer size. We get our buffer by going buffer equals the stream. If the streams if the buffer, okay, so if this, we want to get the streams last node data, probably want to get that node first. There's our buffer, and our buffer size is the buffer cap minus the node size. So that gets a buffer from the stream. If that doesn't work, ADT, I don't know what that means. It's a stream of it's a stream of text data right now, basically, for printf buffering. Oh, no. No, it's a concrete data structure. It's a stream of bytes. Try to get a buffer from the stream. If we didn't get a buffer, make one now. So if buffer is still 0, then what we're gonna do is look at the remaining size is data size minus the position. And so we're going to go alloc size equals, give me the max of stream alloc size and the remaining, let's see, so the alloc size to be the size of one new node plus the remaining size we need to fill. So if we've already got some buffer, we'll fill it with what we can, with as much as we've got. If we come around and we don't have any buffer for some reason, then we're going to create a new buffer node, and we're going to create a new buffer node, and we're going to set its size. We're going to set its capacity to be at least big enough to handle all this, but also not smaller than the default size. And then we're going to go data equals push array onto the stream's arena, 1 alloc size of data bytes. We will put the stream node there first. And so the stream nodes data is the stream node plus 1, whatever comes right after the stream node in the buffer. The stream node's initial size is 0, and the stream node's is queued up inside the greater stream data structure. First node, last node, stream node. Just call this the node now, thank you. So create a node, initialize it, and then we set the stream's buffer cap. To the alloc size minus the size of a stream node. That's how much data is left after we put that stream node in at the header of the block. Now, try to get a buffer from the stream. And then we need to set a buffer still. So the buffer is now node data, and the buffer size is the stream buffer cap. Now, copy amount is the smaller of the buffer size and the remaining size. We're not dealing with commitment issues. Ultimately, we just copy into the buffer. Although we also are going to need a stream node pointer all the way through. So why don't we do... Okay. So that means we assign that to the node there, set the buffer cap, and you come with us. Bingo. And then calculate the amount we can copy that amount. The node size gets incremented by the copy amount. The stream total size gets incremented by the copy amount, and the position gets incremented by the copy amount. And then we recur. This should only ever happen twice now, because on the first pass there might be some buffer sitting around that is insufficient to grab the whole string, and it'll fill some of it there, and then it will loop around and put the second chunk in a separate allocation. Ultimately, it ends up just having to copy one or two chunks of this to one or two places. Now, if I want to, later I can just say, remember some data, instead of having it say, copy it in, okay? Now, this is like a hint. It's basically the same thing as write. I'm just going to pass it like this, actually. In terms of what it means informationally. But in terms of what hint it sends to the optimizer, it's a little different. It's going to say, treat this pointer as if it cannot disappear during your lifetime, and optimize according to that assumption. And what you can do with that assumption is you can say, instead of all of that, you'll just go stream node equals push array stream arena stream node 1 SLQ node SLQ stream first node stream last node node data equals data string node size equals data size stream buffer cap equals 0. So So there you go. Now there's still another question, which is, these are both great concepts, but I think where I'm leaning towards is I might want to allow you to indicate this difference, but still also have a heuristic under the hood. There might be cases in this one where it's just better to write it than to remember it, right? If I pass a small string of 20 bytes or something into remember, it's probably better to just copy that than to remember it. I can't go the other way around. I can't look at this and go, hey, this is huge, I don't want to copy it. If someone says write, you have to write it because we're saying the data needs to be copied. This is permission not to do a deep copy, basically. It's not requirement to do a deep copy. So I might need to separate those out into a layer of low-level commands that are like exactly what you're asking for, and then a higher-level thing that has a heuristic. Don't have that yet, so you got to be careful how you use remember. But I think most of the time, the static cases where remember will be usable will make a lot of sense. So now all I have to do, let's see here. Yeah, that's fine. Yeah, this is actually still needed, but it's gonna be, actually no, it's not. You're out. You're fine. Except instead of blocks, you just look at your nodes. Don't do the node +1 thing, do node data, node size. Exactly, there you go. Very simple. Basically string 8 list at this point. It's pretty simple, pretty close analog to the thing that already was magic. We're just keeping track of the extra buffering capacity that is sitting at the end of the current node all the time. Now what we could do is, if this gets interrupted, right, if we have a big buffer and then someone remembers something in front of it, we could take unused memory and have another spot here that's like stream node free nodes, and they'd be a node, a free node would just be a node like this that's sitting there waiting to be reused, and this would be like the free node buffer cap. And so then if you want to put a buffer in place, you would just see if the current buffer, you take the current buffer first before you do anything else, and this will let you split the stream blocks over and over again. So probably we'll add that trick into place to reuse all the memory as much as possible. But let's keep going on making all this work. Okay. This one, okay, right. So this was also hard-coded right into the thing. Try to get a buffer from the stream. Okay. If buffer size is greater than 0, boom, boom. Actual size equals attempt to print it in here. Else, just do it with nulls. You got nothing. Just give me the size. back, right? We didn't have a buffer ready to go anyways. So if the actual size is less than the buffer size, then we went down this path and we're good to go. So the node, well, we should keep the node. We didn't keep it. We should keep it. The node size and the stream size get incremented. Otherwise, we grab a scratch arena and we just go through the slow path, which will then trigger construction of a new buffer big enough to hold the data, and it'll have to do a copy. Now, if we wanted to, we know the actual size. We could do... We didn't get a buffer. The logic here is we didn't get a buffer. Or the buffer wasn't big enough. If we do it this way, what happens is we waste less memory because we'll construct the string in place and then we will fill. I think we'll do it that way. I think we'll keep doing it that way because this has the possibility of constructing it in place and then using a bunch of memory that's sitting there waiting to be used for the price of a copy. We could eliminate the copy for the price of we could eliminate this copy for the price of possibly skipping over memory that's already sitting there. I mean, it'd be real cool if you could print to a pair of buffers. Like if you could print to a buffer vector or whatever, that an array of buffers that could constitute an output stream or something. So that you could say, like, I got a couple blocks ready for you, fill, and they're together, they're big enough for the whole thing, so let's fill that. But we don't have that in this function. Okay, so allocate ahead and commit allocation actually got pulled out. Block read also got pulled out. This exchanges block for node. Node data, node size, position plus equals node size. Yeah, easy enough. Okay, peak last char is interesting. If node does not equal 0 and node size is greater than 0, then give me node data U8 node size -1. Very good. Let's go back over to this code base now because I broke the ASCII stuff a little bit when I took out the allocate ahead. My idea here is now, instead of saying I haven't really considered it. I know C is frustrating, but I don't think the other languages are going to be very much less frustrating in the ways that matter. Most of what's frustrating to me isn't the language as much as the entire environment of computing that I'm trying to work with. That's what's frustrating, I think. But I could be wrong. Maybe it's the language. Stream grid size. Okay, so Well, what if I did just use the allocate ahead concept still? And I'm not sure why I thought it would work super easily without it, but I still need to tie the new memory into the stream, which means I need to use the stream's arena at the very least. Like, the only way I could use what I have here is if I'm allowed to go... This becomes push array stream arena U8 grid size. So I just grab memory off from the stream's arena, and then at the end I can say stream remember stream straight grid size. Right, I guess that works. So I'm putting the memory onto the chain. And so this is something like stream allocate stream grid size. That seems good. Because then what we'll do here, let me send you some links. And yeah, I did talk about this a lot yesterday, and I think I was interested in talking about it yesterday, which is not always how I feel. Like today, I'm actually needing to wrap up in the next few minutes. I don't have the luxury of hanging out all day. But here we go. Okay, so that gets us farther. Now the only downside is when this is being used as a data structure, it's gathering up data all the time, it's churning memory, so this makes perfect sense. We can just allocate some extra stuff on the side that isn't in the stream, fill it, and then stick it into the stream after the fact. But if it's gonna wrap a file stream, then where's the arena? Like, is there still going to be an arena there? If there is, how does that work? It just sits there and gathers memory, but there's no point at which this stream... I guess the stream gets closed eventually. But the weird thing is that the memory should be temporary. So the moment you remember the memory here... that you allocated here, you stuck it where it needs to go. You don't, if it's a file stream, I'm just going to write that, and then I should probably release it. So the question is, how is that going to work? If it's an arena data structure growing underneath, then there's no freeing it. But if it's remembered, then it needs to be freed. So maybe the allocate ahead approach was correct, and the remember trick. Yeah, I think it should just be you do allocate, and then you do commit, and you commit the previous allocation to the stream. So you allocate, commit. I think that feels like the most reasonable interpretation. Like that sorts this out. So remember is a trick, and then void function void stream commit stream looks like this. So remember goes like this, and then stream commit is where you take a stream. What we're going to do is in the stream itself, I think we'll have to do is we will remember an allocation and an allocation size. And so here we'll set the stream's allocation to this, and the stream's allocation size to this. And then this is just saying stream remember the allocation. And then clear that out as well. And the reason to do it that way is so that if you use allocate, you always pair it with a commit. And if this is a file handle under the hood, then remember just does write because it can't do anything else. But commit and allocate do make a temporary allocation and then use it and release it, which can actually totally go fine hand in hand with the file handle. We'll just set up a small arena. The last the function keyword just means static in C. It marks it's you have to mark your functions, right? And I default mark them as static. But then if I want to link them, I have I think it's a linked function. And if I want a shared function, I think, is it shared or dynamic function? Yeah, dynamic function. So I have a couple other kinds of functions. But function is just static. Okay. So there's everything working. Commit is just a closure for the allocate API, so that this can work with a file stream. Remember is for saying, hey, this data doesn't need to be copied. You could just make a mini node. Now, what's left to do is right here, after remembering something, you could reuse the portion of the buffer that you haven't actually used yet. So what we could do is say stream node unused node U64 unused buffer cap. And so what'll happen when you do this is we'll set those first. The stream unused node and unused buffer cap will work like this. First we have to get the data back. So we're looking at if the stream has a last node, Then we're looking at the unused data, which is the last. Let's grab this node. Data plus node size. And then, of course, the unused size is the stream's buffer cap minus the node size. Now, if the unused buffer cap, call that buffer size, is greater than a stream node, then we can keep it around. So, and let's say it needed to be greater than a stream node, plus it needs to have like at least 16 bytes. Okay, we don't want to fight for too many scraps here. So the unused node becomes the stream node that you find right at the beginning of the unused data, and the unused buffer cap stream node, unused node. That's the unused node. And the unused node already has its data. That's the unused data. Well, that's just the unused node plus 1. And it also has its unused size. Leftover buffer size is the unused buffer size minus the size of the unused node that we put at the beginning of it. That tells us how big that is and how big that is. So, no. This is a size of 0. The node is empty. It has a data, the unused buffer cap. We don't really need both. The unused node looks like that. Now, if you go to this block, if we didn't get a buffer, make one now. If we didn't get a buffer, try the unused node. So the buffer cap was 0. It becomes whatever's sitting in that unused node, and the node size gets set back to 0, so that we can then use this to make our buffer. If that doesn't give us anything, oh, and then we should probably set the unused node to 0 as well. That gets us an unused node, and we also need to queue that node up into the stream at that point. And then it's good to go. So this should set up a system where we set up some memory, a memory block, we fill it, and then if we have something that we quote unquote remember, we inject some data from elsewhere, no problem. You inject the data, and you do that by setting up a new node You chain the two nodes together and point at that data you're injecting. You're saying this just gets stuck in the middle. The unused memory that was in the first block gets set aside, and the next time we do allocate a new buffer, so now we could remember several things in a row, we won't touch it. But the first time we come through here and we're trying to get our hands on a buffer, it'll grab the buffer that we set aside and keep going. So the only thing we lose is that another node got put in, split into the buffer. But this way, the memory we allocate never gets thrown away in this stream system. And we minimize the number of times that we might end up touching the arena a lot further. Because we don't have to go to here. Yeah. Okay. Cool. And these here are using remember, whereas these here are using write. So we should be able to see this if we want to. This is main again. Test. So here we print a new line. Here we... Oh, but we're not putting it all into one big stream, are we? Okay. Well, that... I always love it when arenas shine like that. That really... went very well. Show me. Okay, well that's clearly wrong. Who said you could do that? Is that me? Try to get a buffer from the stream. How is there not some kind of... there's nothing there that makes sense. That's a little concerning. What did I do? Buffer node. Try to get a buffer from the stream. Try to get a buffer from the stream. Okay, so these are supposed to be zeros. That's the problem. These are initialization code that's supposed to be included only inside the braces here. Last node, buffer, size. There we go. Now I should be able to see, okay, here, we come in here, we've got no buffer set up at all yet, so we end up putting it onto a Scratch arena and we write it using the old-fashioned write function. Now, why do we have unused data in the stream already? I'm confused. Let's start from the beginning and walk through this again. I'm a little unsure. So the stream initially looks like this. Good. We arrive here, and the stream now looks like total size of 1. Set up a buffer cap. Okay, so that's all seeming right. Why did it look so wrong before? What did I misunderstand? This does nothing, this does nothing, this does nothing, this does nothing. Right is right here. Data size, position 1, stream. Okay, it is empty. There's nothing. Okay, I don't know how we ended up with an unused. I think I might have been in the wrong iteration of the, might have been the second time it got called or something. So we set up a new buffer. Copy one over, and we're done. Now we print some other stuff. The stream should now have 2 nodes here, but the total size didn't go up. That's part of the mistake. So the stream, when we remember something, needs to increment its total size. Okay, I think that might have been part of why I was confused. So when I get to here, the stream should look like, yeah, it's got a good number of characters in it. It's got a first node, which is like stream first node data. You can't show me that, or you don't know what type it is? Okay. If I tell you this. There we go. Okay, so it's a new line character, but you don't print them that way. Okay. Yep. And then yeah. We come through here. Eventually we're gonna arrive at, I skipped it again. But I should have a third node here. The buffer cap. Okay, the buffer cap is the clue I need. The stream buffer cap versus 16 megabytes. 16 megabytes minus stream buffer cap. Right. Stream node. Okay. So we take the unused data, we make a pointer variable, we align buffer cap. That's actually just unused data plus buffer cap as a thing, but unused buffer size plus that. Okay. Yeah, that's good. Pointer aligned. Now, question isn't if unused buffer size is greater than this. The question is if unused OPL minus unused is that greater than unused putter aligned? And if it is the difference greater than or equal to the size of a stream node plus 16? If it is, then putter from int unused putter aligned. We have to do these alignment thingies. Okay. Unused pointer aligned. Leftover buffer size. That minus the size of a stream node. Okay, that should avoid any alignment issues. So now, if I get this far, I've got 3 nodes. I want to see, yeah, the buffer cap is 0. If I do this, and I step in here and I don't screw it up, I think it won't be able to do this because the buffer cap is 0. So it's going to do actual size, and then it's going to come in here. And the size here is 1. And it's going to do unused node. Buffer cap. Stick that in the chain. Okay, so just to see if that makes sense, 56, what's the size of a stream node? 24. So the size of 2 of those is 48. That means there's 8 more bytes. That's 1 byte for the first new line we printed plus the 8 bytes of alignment makes it 8. And now if I do this, total size goes up, I run out of buffer cap, then I do this. Now it's just, it's up another 56 plus another 8. Looks like that's all working as it should be. Cool. Cool. All right, I think this is a good spot for me to wrap up today. This feels pretty nice. So the main thing this does is it pretty much works like a string list, and I can just drop strings into it like I used to be able to do without having to copy them in by using this remember trick. And I can even do things like not have to use the stream to allocate and then commit memory into the stream as a single write operation, so that I can do things like set up a grid. Why is that called grid size, though? That should be called size now. Stream allocate should just take a size parameter. Grid size was from the use case where that evolved out of. Okay. And then the writing functions over here allow you to copy data in or to use format strings to copy data in, and it buffers them up rather than having a bunch of separate nodes. You kind of get the best of both worlds, hopefully. It also just means you have to create a new one and release it. They're not lightweight to create and destroy. Making that one trade-off meant that it was super easy. And you know what? Maybe that's the right way to do it. Maybe I don't construct really tiny strings, and if I do have lots of little string constructions to do, I can always create one stream and then clear it, and that's much cheaper. Or at least it could be. Arena clearing might be just as expensive as Arena releasing, but at least it's not as expensive as constructing a new one from scratch. Either way, that's it for today. I do not expect to do more streaming tomorrow, but I've been in a real streamy mode, so maybe I'll show up and do something. But there are plenty of things going on right now. I'm working on this ASCII layer. I'm working on this stream layer that I just set up. So check that off the to-do list. And I got the RPG simulator stuff going on, so I don't know exactly what the plan is, if I'll stream tomorrow or not. But definitely next week I'm going to start getting into object file stuff. That's my plan. So now that I've got table printing ready to go with this layer, I'm going to swerve over and make sure, get all my PE parsing stuff up to like current in my head, so that I can write a new tool that I want for visualizing and exploring something that I was doing with the RPG simulator. And so that's what I'll be touching starting next week. All right. And with that, thanks for coming and seeing what I'm up to and hanging out. And I'll see y'all around the internet later.